Okay, I want you to picture something for a second. We're going to start with a little mental experiment. Imagine you're standing in front of a massive bonfire. It's a pitch black night, cold air, but this fire is just roaring.
Okay, got it.
You're standing right up close to it, maybe a foot away. You can feel that intense crackling heat on your face, maybe even singing your eyebrows a little bit. It's unbearably hot, right?
Naturally, you're standing right next to the source of the energy.
Exactly. So you take a step back.
Yeah.
And then another step, and another. You walk 10, maybe 20 feet away from the flames. What does basic logic or just your survival instinct tell you should happen to the temperature?
It drops. That's thermodynamics 101. Distance equals cooling. The further you are from the energy source, the colder it gets.
Right. It's intuitive. It's how the universe works. But now imagine that as you take that step back, instead of cooling down, the air suddenly gets hotter. And you keep walking away. And it's not just getting a little warmer, it's scorching. By the time you're 50 feet away, the air around you isn't just bonfire hot. It is millions of degrees hotter than the fire itself.
Yeah.
You'd think you were hallucinating.
You would think the fundamental laws of physics had just broken down in front of you.
Well, welcome to the sun. Because that impossible scenario, that is exactly what is happening in our solar system right now. It is called the solar corona mystery, and it has been driving scientists absolutely up the wall for over 80 years.
Up the wall is putting it mildly. This is arguably one of the biggest open questions in astrophysics. It's a paradox that completely defies the intuition we use to navigate the world.
Yeah.
You expect heat to dissipate, not to spontaneously multiply the further out you go.
So today on the Deep Dive, we are exploring a major breakthrough in this mystery. We are looking at a study published in Nature Astronomy that might finally explain why the sun's atmosphere is baking hot compared to its surface. We've got data that gathered dust for 3 years, explosions the size of countries, and a concept called nanojets.
It is a fascinating story. It's partly about the physics of magnetic fields, sure, but it's also a story about patience. And about looking at the sun in a way we never had the resolution to do before.
Let's set the scene first, because I think people know the sun is hot. That's not news. But I don't think they realize how weird the structure of that heat is.
Right. To understand the mystery, you have to look at the layers. So let's trace the journey of energy. The sun's core is the engine. That is where nuclear fusion happens. We're talking roughly 15 million degrees Celsius.
Okay.
Unfathomable heat.
15 million. That is our baseline. That's the furnace.
Correct. Now, as that energy radiates outward, it fights its way through the different layers of the sun. By the time it reaches the visible surface, the part we can actually see, which is called the photosphere, it has cooled down significantly.
Right.
It drops to about 6,000 degrees Celsius.
Which is still hot enough to melt. Well, everything.
Yeah.
But relatively speaking, that is a massive drop. From 15 million down to 6,000.
Exactly. And that makes sense. The energy is spreading out. It's escaping into space. But here is where the logic breaks. If you keep moving outward, away from the surface and into the solar atmosphere, the solar corona, the temperature doesn't continue to drop.
This is the bonfire moment.
It is. You move a few thousand kilometers away from the surface, and the temperature violently spikes. It shoots back up to 1 million, sometimes 5 million degrees.
That is the part that breaks my brain. One of the sources used the analogy of boiling a pot of coffee. It's like the coffee inside the pot is boiling, but the steam rising off it is somehow superheated plasma hot enough to melt a spaceship.
Or moving your hand away from a candle and getting third-degree burns the further back you pull your hand. It implies that something is adding energy to the atmosphere after it has left the surface.
Right.
The sun is effectively heating its own halo, but for decades, nobody could figure out the mechanism.
For 80 years, we've been staring at the sun for a long time.
We knew something was heating it, but we couldn't see what. It was invisible to our instruments. The corona is, wispy and faint compared to the brightness of the surface.
Okay.
It was like trying to see a match being lit next to a spotlight until, potentially now.
Enter the protagonist of our story, Patrick Antolin.
Yes, a Colombian-French researcher. And honestly, his part in this story is a great reality check on how science actually works. We tend to think of discoveries as these instant eureka moments where a guy looks in a telescope, gasps, and, calls the president.
Like in the movies. Dramatic music swells, and the answer is obvious.
Right. But real science is often about administration, delays, and dusty hard drives. So Antolin is looking at data from the IRIS satellite. IRIS is a NASA solar observatory specifically designed to look at the interface between the sun's surface and its atmosphere.
And he spots something back in 2014.
He does. He is reviewing a catalog of images, and he notices these strange, tiny, jet-like bursts in the corona. They didn't look like anything standard. They weren't the big solar flares we were used to seeing. They were small, sharp, and fast. His intuition told him, this is big. This is anomalous.
So naturally, he dropped everything, locked himself in a lab, and solved it that week.
I wish. No, he was busy. He had other grants, other papers, other deadlines. This is the human element we forget. Scientists have schedules.
Right.
He literally printed the images or kept the files marked, and they sat on his desk.
Gathering dust.
For 3 years. The answer to an 80-year-old mystery was sitting next to his coffee mug while he did other work. It wasn't until 2017 that his supervisor in the UK basically gave him the green light, the funding and freedom to focus exclusively on this weird data.
I love that detail. It makes me wonder how many other scientific breakthroughs are currently sitting in a to-do pile on some grad student's desk right now.
Probably more than we want to know. But once he finally dug in, he reconstructed the event. And what he saw was a distinct 3-stage process that plays out in the solar atmosphere.
Okay, walk us through these stages. What does a heating event actually look like?
So visualize a loop of plasma arching off the sun, like a giant magnetic rainbow made of fire.
Okay.
Stage 1. Antolin identifies a specific section of that loop that is cold.
And when we say cold?
We mean astrophysical cold, about 60,000 degrees Celsius. In the context of the corona, that is freezing. It's a cool pocket of gas.
Got it. Stage 1, cool pocket.
Stage 2, the explosion. He observes a series of incredibly fast, thin bursts of energy. He called them nanojets.
I want to put a pin in the word nano for a second, because words matter. When I hear nano, I think of iPods or nanotechnology or microscopic robots. I think small, cute almost.
In the context of the sun, they are small, but that is only because the sun is 1,000,000 times the size of Earth. In human terms, these things are monsters.
The stats in the report are actually terrifying. We are talking about speeds of 700,000 kilometers per hour.
Hypersonic speeds.
Yeah.
And they're fleeting. Each burst lasts less than 10 seconds, but the energy output is the real headline here. This is the part that blows my mind. A single one of these nanojets releases energy equivalent to about 2,000 nuclear bombs.
Wait, hold on. 2,000.
Roughly the yield of the bomb dropped on Hiroshima multiplied by 2,000. In a burst that lasts a few seconds.
That is distressingly powerful. That's not a nano anything. That's an apocalypse.
It is. And remember, stage 3. After this explosion, that cold pocket of gas, it instantly heats up to millions of degrees. Antolin watched the temperature spike in real time. Cold, explosion, hot.
Wow.
It was the visual proof of energy conversion.
But it wasn't just one pop, right? The source mentions an avalanche.
Exactly. Antolin found that these nanojets trigger a chain reaction. In the specific event they analyzed, they counted 150 of these explosions in a span of just 10 minutes.
So do the math. 150 explosions, each packing the punch of 2,000 nukes, all going off in a confined area in 10 minutes.
Precisely. It is like setting off 1 billion space heaters at once. You are dumping a mind-boggling amount of energy into the local atmosphere, and that explains why the temperature shoots up.
Okay, so we have the what, we have the explosions, we have the heat, but we need to get to the why. The sun isn't just detonating for fun. There has to be a mechanic driving this. The report mentions a magnetic spider web. Can you unpack that?
This is the most beautiful part of the theory. It connects the chaos to the structure. To understand the sun, you have to stop thinking of it as a solid ball. It's a fluid. It's plasma. And it is threaded through with magnetic fields.
Antolin's analogy was a spider web, but a spider web where the anchor points are moving.
Right. Imagine a spider web where the wall it is attached to is actually a churning, boiling ocean. The sun's surface is constantly moving, bubbling up and down with convection currents. So what happens to the web sitting on top of it?
It gets tangled.
It gets twisted. The threads, which are the magnetic field lines, get braided together. They get pulled tight. Think of a rubber band. If you twist a rubber band over and over and over, you are storing potential energy in it. It gets tighter and tighter. It vibrates.
And eventually it snaps.
Eventually, the tension is too great. The magnetic lines snap and realign into a simpler configuration. In physics, we call this magnetic reconnection. And when that snap happens, all that stored energy has to go somewhere.
It goes into the nanojet.
Bingo! The magnetic energy is instantly converted into kinetic energy and thermal energy heat. That snap is the jet.
So the impossible heat of the corona is basically the energy of a billion snapping rubber bands being released at once.
That is the leading theory. It is mechanical energy from the surface churning, stored in the magnetic field, and then released explosively in the atmosphere.
It creates a direct link. The motion of the surface causes the heat in the atmosphere.
It's fascinating because it connects back to a theory from the 1980s, right? This wasn't a totally new idea.
No, and we should give credit where it's due. A physicist named Eugene Parker proposed this decades ago. He called them nanoflares. He predicted that the corona was being heated by millions of tiny magnetic explosions.
But he couldn't prove it. He didn't have the eyes. The telescopes back then couldn't see something that small or fast. Parker knew the math worked, but he had to wait for the technology to catch up.
Right.
Antolin's nanojets are effectively the visual confirmation of Parker's nanoflares.
So, case closed. Mystery solved. Can we pack up the telescopes and go home?
You know, science never worked like that. There's always a yes, but.
Who is the but in this case?
Well, the scientific community is cautiously optimistic, but there is skepticism. The source highlights Ada Ortiz-Carbonell from the University of Oslo. She agrees this is a massive step forward. It is the first time we've directly linked a flash to heating. But she points out that the sun is a messy, complicated place. Most solar physicists believe there isn't just one heater. There are probably waves, magnetic pulses, and other mechanisms working alongside these nanojets.
So nanojets might be a piece of the puzzle, but not the whole picture.
Correct. And there is a statistical problem. Antolin saw these jets in a very specific, active loop of the sun.
Right, he got lucky. He was looking at a stormy part of the sun.
Extremely lucky. But to explain the global temperature of the corona, why it is hot everywhere all the time, these explosions need to be happening everywhere, even in the quiet parts of the sun.
And we don't have proof of that yet.
Not yet. NASA says these are strong candidates, but until we can point the camera at a quiet patch of the sun and see the same fireworks, we can't say for sure that this is the answer.
The victory condition, as Antolin calls it.
Exactly. If they're ubiquitous, we win. If they are rare, they are just a cool anomaly.
I want to pivot here because I think it is easy to get lost in the numbers. 15 million degrees, magnetic webs, nuclear bombs. It all feels very abstract. Why does this matter to me sitting here in my studio worrying about my commute or my grocery list?
That is the question I love most. Because usually when we look at the sky, we feel small and separated from it. The sun is 93 million miles away. It feels like a background object.
A light bulb in the sky.
Right. It's over there. We're over here. But Patrick Antolin makes a really profound point in the interview. He argues that Earth is not separate from the sun. In fact, physically speaking, Earth is orbiting inside the solar corona.
Wait, we are inside the atmosphere?
Technically, yes. The solar wind, the particles, the magnetic influence, that atmosphere extends way past Earth. We are living in the outer edges of the sun's environment.
That is a terrifying thought. It makes it sound like we're in the belly of the beast.
He uses the analogy of a kite in the wind or a stone in a river.
Yeah.
We are sitting in a stream of particles that is continuously flowing out from the sun.
So if the river gets turbulent,
the stone feels it. This is what we call space weather. When those magnetic webs snap and release energy, they don't just heat the corona, they accelerate particles toward Earth.
Which can mess with satellites, GPS, power grids.
All of it. If we don't understand the mechanism, if we don't understand how the magnetic field snaps and releases heat, we can't model the weather. It is like trying to predict a hurricane without understanding how evaporation works.
So solving the nanojet mystery isn't just about satisfying curiosity. It is about protecting our infrastructure.
It is about survival in the environment we live in. We are swimming in the sun's wake. We need to know how the water moves.
It really changes your perspective when you walk outside. You're not just feeling the heat, you are feeling the downstream flow of these magnetic explosions.
Ideally, yes. Though I wouldn't recommend staring at the sun to check for nanojets.
Please don't do that. Before we wrap up, I have to touch on one little nugget from the research that I found surprisingly timely. The word corona.
Ah, yes. The word of the decade.
Obviously, for the last few years, that word has had a very specific medical association for all of us. But the astronomical term is way older.
Much older. The source mentions it dates back to the 18th century, but was formalized by a Spanish astronomer, José Joaquín de Ferrer, around 1809. Corona is just Latin for crown or wreath.
Because during an eclipse, that is what it looks like. A white crown around the black moon.
Exactly. And the connection to the virus is purely visual. When virologists looked at the coronavirus under an electron microscope in the 1960s, they saw these little protein spikes sticking out.
And they thought, hey, that looks like the solar corona.
Right, so the virus was named after the sun, not the other way around. It is a little etymological full circle.
So let's bring this deep dive in for a landing. We started with a paradox. A star that gets hotter the further away you get from the fire.
We found the missing link in a stack of dusty files on a researcher's desk, proof that patience is just as important as genius.
We identified the culprit, nanojets. Tiny hypersonic magnetic explosions that act like thousands of nuclear bombs going off every few seconds.
And we realized that these explosions are the engine that drives the space weather hitting our planet every single day.
It is a reminder that even the things that look stable, like the sun rising every morning, are actually incredibly violent dynamic systems when you look close enough.
And that sometimes the biggest discoveries are just waiting for someone to have enough free time to look at the pictures.
Antolin's victory condition is still pending. We're waiting for the next round of data to see if these jets are happening everywhere. But for now, it looks like we are one step closer to understanding the fire we are all warming our hands by.
Couldn't have said it better.
Thanks for listening to this deep dive. Stay curious, and we will catch you on the next one.